Okay, so we will start off. See,
We did.
we did, yeah, that's where we started. Then I came to triangles.
Yes, sir.
But let me start off with the 2 point charge systems, which we generally do in our classes, generally in JEE classes. That's a very common thing that is done. So, question number is what? 25.
Yes, sir.
Okay, so we'll start off with question number 25. See, this is a very common scenario, and uh, there is no extraordinary thing that we are doing over here. Everywhere, all over the country, everyone does this. Okay, so it's a very simple thing. So let us say we have 2 points A and B, and we have charges plus Q1 and plus Q2 placed at the points A and B. Okay,
Yes, sir.
let the distance between points A and B be small a.
Yes, sir.
Now, the question is find find a point, find a point or points. Okay, find a point or points where net electric field is zero, and we need to find these points on what? On the line, extended line AB. On the extended line AB means anywhere on this line AB. Okay, on the extended line AB, we need to find a point
Mm.
on this line somewhere where the net electric field due to charges Q1 and Q2 is zero. Okay,
Yes, sir.
because we know it is given that these two are positive charges. Understand one thing, if we choose, let C be that point. Okay,
Yes, sir.
let C be the point. So if I choose a point C somewhere in between A and B, field due to Q1 at point C will be from left to right,
Yes, sir.
and its magnitude will be something like E1.
Mm.
And field due to Q2 at the same point C will be from right to left.
Yes, sir.
Directions of E1 and E2 are opposite to each other. So what we say is, for net electric field to be zero implies the magnitudes of E1 and E2 should match each other, right?
Yes, sir.
And because of opposite directions, they will cancel each other. Therefore, we can say that the electric field at that point is zero. Okay.
Yes, sir.
So we are saying let that point be C. Let C be that point, and AC is equal to X, some random X.
Mm.
We need to find this X only. Okay.
Yes, sir.
Is this clear?
Yes, sir.
This distance from A to C, I am taking it as X. So what will be the distance from C to B?
AB minus
And AB is small a, right?
A minus.
A minus X. Now tell me, what is the electric field due to Q1 at point C? Is K Q1 by
It will be X square.
X square. What is the field E2 due to Q2?
And C will be K Q2 by A minus X
A
whole square.
minus X whole square. And for net electric field to be zero, these two should
We
be
have
equal.
to equate.
We have to equate these two. I'll just show you the solving of this. So basically LHS is equal to RHS, So k q1 by x square is equal to k q2 by a minus x whole square.
Hmm.
K will cancel each other. Okay.
Yes, sir.
On cross multiplication, I am bringing a minus x to the numerator. So a minus x by x whole square will be my LHS,
Yes, sir.
and RHS will be q2 by q1.
Yes, sir.
Now doing square root from here, I'll have a minus x divided by x is equal to under root of q2 by q1.
Hmm.
That is implies a by x minus 1 is under root q2 by q1.
Yes, sir.
So therefore, taking it on the other side and doing cross multiplication, my final answer I'll get it as a divided by 1 plus square root of q2 by q1. Is this clear?
Yes, sir.
So the point where the net electric field will be zero due to the charges q1 and q2 will be at a distance of x, which is nothing but a divided by 1 plus square root of q2 by q1 from point A. Okay,
Yes, sir.
towards right side. Is this clear?
Yes, sir.
Xerox. It can be either plus or it can also be either minus, right?
Done, sir.
So what you're saying is when I take this under root, I need to know if it is, I mean, I should put plus or minus because square of plus and minus both will be right.
Hmm. Yes,
Now
sir.
here comes understanding literally how the effect of plus and minus is going to take place. Suppose if I have negative
Hmm.
1 minus something is going to be negative or it is going to be less than 1. So one thing is sure, it is less than 1.
Yes, sir.
Anything divided by less than 1, if it is between 0 and
That
1,
distance can't be
is
greater. That's a
greater than a. If it is between 0 and 1 also, it becomes overall x will become greater than a.
yes, sir.
Then x will cross the point b, which is not possible.
Hmm.
See, if you choose a point on the left side, the electric field due to q1 is also in the same direction and q2 is also in the same direction.
Yes, sir.
If we choose a point on the right side of b, the electric field due to q1 and q2 are in the same direction.
Hmm.
So to the left of a or to the right of b, it's impossible for me to attain equilibrium, or let's say attain zero electric field.
Yes, sir.
But if I choose some point in between, then it will definitely be the right answer, correct?
Yes, sir.
That means x for me cannot be negative, first thing, and also x cannot be greater than e.
Hmm.
So if I choose minus, in that case, the two possibilities is either the entire x will be negative or x will be greater than a, and either
Yes,
of them
sir.
is not possible.
Hmm.
Therefore, it cannot be minus.
Yes, sir.
Also, if q1 is equal to q2, 1 minus 1, it will give me undefined.
Yes, sir.
1 minus 1 will become 0 and a by 0 will become undefined. So basically that's the reason I am not taking the plus or minus thing over here. But good question. Okay.
Yes, sir.
Now I want to just extend this a little bit and I want to discuss something related to this. So we said field is a point where if you put a test charge, its product with charge will give you force,
Yes, sir.
right?
Yes, sir.
So if point C is the point where the net field is zero, yeah,
Mm.
one second. If the point C is a point where the net field is zero, that means that if I place a test charge, if a test charge Q is placed at C, what will be the net force due to Q1 and Q2 on charge Q?
Wait, just a moment.
Net force will be charge times the field, right?
Yes, sir.
What is the field at point C? We found point C by making the field zero.
Yes, sir.
What is the field at point C?
Zero.
Zero. If the field is zero, then if I place a test charge at point C, the force on it will be what?
Zero.
That's why just now I said another thing. Can I say that this is equilibrium position?
Yes, sir.
Yeah,
Yes, sir.
something is happening to my English. Very good. So we can say that this can also be said that it is equilibrium position because net force is zero, right? Wherever we find net force is zero in mechanics, we say it is a equilibrium position, right?
Yes, sir.
The definition for equilibrium position is net force is zero.
Yes, sir.
So understand the entire story right from the beginning. There are two charges Q1 and Q2 placed at points A and B. Find the point C where the net electric field is zero. So we said let the distance A to C be x. So net electric field over there will be zero. That means E1, which is from left to right, should be equal to E2, which is from right to left.
Mm.
Cancel each other, do under root things, get the answer x is equal to A by 1 plus square root of Q2 by Q1, right?
Yes, sir.
So therefore, we have found the point on the line extended line AB where the net electric field due to Q1 and Q2 is 0.
Mm.
If a point charge test charge which is Q is placed at that point, then the net force will also be 0 because force is nothing but the charge placed over there into the field.
The field.
Field over there is 0, therefore the net force is 0, right?
Yes, sir.
If the net force of is 0 at a particular position or at a particular situation, we call that as equilibrium position.
Yes, sir.
So I can say that this point is equilibrium point or equilibrium position because the net force on a test charge placed over there is going to be 0.
Mm.
Now a little bit like I said, the wherever we get the use of mechanics we will be discussing it in these in chapters also, right?
Yes, sir.
Whenever you say equilibrium position, that means there are two types of chances. One is the equilibrium position can be a stable equilibrium or the equilibrium position can be an unstable equilibrium.
Mm.
Correct?
Yes, sir.
For equilibrium position, so we found out where the equilibrium position is. The equilibrium position, so what I am saying is if the question is given there are two charges placed q1 and q2 at a distance of a, find where a third charge q should be placed such that the charge q is in equilibrium with q1 and q2, right?
Yes, sir.
Also, these charges Q1 and Q2 are fixed charges. Okay.
Yes, sir.
So in terms of force, if I create a question like that, still the solving will be the same and we will still get the value of x as the same. Okay.
Yes, sir.
So find the point where I should place the charge q such that the net force is 0. So we will say the point where it should be placed is x, which is at a distance from a towards right, and that is a by 1 plus square root of q2 by q1.
Yes, sir.
This point C is the equilibrium position in this particular situation. Correct?
Yes, sir.
Now there are two choices for equilibrium positions. One is stable equilibrium and the other is unstable equilibrium, right?
Yes, sir.
So either of them are possible, both can't be possible together.
Mm.
Either stable equilibrium or unstable equilibrium is possible, right?
Yes, sir.
If he will ask me, is this a stable equilibrium, how will I figure it out? Oh,
Differentiate.
no, too much of, yeah, I don't know that much of physics. So, no. So, if it is a stable equilibrium or unstable equilibrium, how we figure it out is by creating a movie in our head. So, what is this movie? If it's a stable equilibrium, that means along the line AB, if I will move, the charge should try to come back to its original position. Then we will call it stable equilibrium.
Yes, sir.
If I externally move the charge Q along line AB anywhere towards left or towards right,
If it doesn't come back.
the charge should try to come to the original position, correct?
Yes, sir.
Then I will say it is stable equilibrium.
Yes, sir.
If I move along the line AB somewhere
Mm.
and if the charge goes away,
Mm.
that means it is an unstable equilibrium.
Yes, sir.
Or mathematically, if I have to say, when will I say it is a stable equilibrium?
It's like when we draw two graphs, like from in the U shape or the reverse U shape. If we put a ball into it, if it comes back into the position, original position, it's stable. If we put a reverse U, then it directly goes away.
That U that you're talking of is a bowl.
Um, yeah, I mean, I told it with respect to a graph.
Yeah, that's fine. So you
Yes,
have a bowl and you have anything, some object.
yes, sir.
Now, at the bottommost position, this object is going to be in equilibrium because it is not going to jump away by itself from here, correct?
Yes, sir.
Same thing will happen in a reverse bowl also. If I place something on top of it, at the exact top point, the
It
thing
is stable.
will be in not stable, will be in equilibrium.
Yes, sir. Yes.
Both are equilibrium positions. Equilibrium positions. But one is stable equilibrium position, other is unstable equilibrium. Which one is stable equilibrium?
The first one.
The first one is the stable equilibrium. How do we say this? If I push this ball
Comes
somewhere,
back.
it will come back to the bottommost position. Whereas if I push this ball anywhere, it will never come back, it will always go away.
Yes, sir.
Both are equilibrium position. So one important factor you have to know, the only definition for equilibrium position is that the net force should be zero.
Yes, sir.
There is no other thing required to define an equilibrium position. Net force should be zero. That's it.
Hmm.
Okay. In under these equilibrium positions, we have two choices. One, it can be either stable equilibrium or it can be unstable equilibrium. So to check if it's an equilibrium position or not, we have to see if the net force is zero.
Yes, sir.
To check the stable equilibrium or unstable equilibrium, we have to start rendering the movie in our head, that if I move it slightly, will it come back to its original position? Will it come back to its equilibrium position, or will it go away and
Hmm.
never come back to its equilibrium position? If it comes back to if it comes back to its original equilibrium position, it's a stable equilibrium.
Sir, so there we talk about the point C moving.
Point C is not moving, charge is moving.
Yes, sir. Yes,
So
sir.
if I move the charge towards right or towards left along the line AB, what will happen is what I have to figure out, right?
Yes, sir.
So first, what stable equilibrium is, if the ball will come back to its original equilibrium position. Second, unstable equilibrium, when I move it slightly, it will never come back to its original equilibrium position. That is unstable, correct?
Yes, sir.
But both are equilibrium position, right?
Hmm.
Let me define it in a mathematical sense, what a stable equilibrium is and what a unstable equilibrium.
Yes, sir.
For a stable equilibrium, see, for both stable or unstable equilibrium, give a delta x. What is this delta x? Delta x is displacement.
Yes, sir.
Displace this particular thing slightly somewhere.
Hmm.
It can be right side or left side. That's why I put the bar. I'm showing it as a vector. Now it's your choice where you want to take it. Similarly,
Yes.
this charge also either right side or left side, that is my wish, your wish. You want to do whatever you do. So you give a small displacement of delta x. If it's a stable equilibrium, if I give this delta x towards right, this is point C. If I
Yes,
give
sir.
the delta x towards right, then for it to be a stable equilibrium, the force should be in which direction?
In the opposite
In
direction.
the opposite direction, so that it can come back.
Yes, sir.
Similarly, continuing this story for stable equilibrium, if I go towards this side, then the
It should
force
be
again
towards
should be,
right.
again it should right. So the idea is, for when I give a displacement delta x, for a displacement delta x, my net force vector should be anti-parallel to delta
Hmm.
x. If it is anti-parallel to delta x, then it will be stable equilibrium.
Yes, sir. Yes.
Now, if I move it right side, anti-parallel force should be left side. If I move it left side, anti-parallel force should be right side.
Hmm.
For a small displacement delta x, I can say it's a stable equilibrium if the resultant force is anti-parallel to delta x. Similarly,
Hmm.
for unstable equilibrium, how will I mathematically define it?
The force and the displacement are along the same. I
Correct.
mean, they're parallel.
They are parallel. So the force vector, net force vector, if it is parallel to the displacement vector that we have given, then it is going to be a unstable.
Sir, but in the stable equilibrium, if we give a lot of force, then it goes out of the bowl. So that will become unstable again.
Your point is correct that for stable equilibrium, if we give a lot of force,
Yes, sir.
we are giving a delta x, not a force.
And then if we do
To
it
give delta
a
x,
very big delta X.
I agree. Yeah. So you're saying if we give a bigger displacement,
Yes, sir.
you're right. I mean, we have a bowl, we have a ball. If I take this ball to China, will it come back? It's a good question. That's why I
Yes,
wrote
sir.
delta x, not x bar,
Yes, sir.
so that you can just take a small displacement and study it. rather than giving huge displacements and then figuring out what is going on.
Yes, sir.
So if you give huge displacements, then it is difficult to discuss because you don't know what is huge. For some people, 1 kilometer might be very small. 1 kilometer can also be delta x if we are studying in terms of billions of meters. But if I am talking for me as a human size, 1 millimeter, I can say it's a delta x. For
Hmm.
an ant, 1 millimeter is like 1 kilometer.
Yes, sir.
So the idea is that we can never be sure about what this delta x value is. It huge or less? That is a big problem. That's why we just define for a small delta x. That means compared to a, it should be slight, and leave it. Give a small displacement and leave it. Then what should happen? If it's coming back, it's a stable equilibrium. That means if the net force is opposite to the delta x bar, anti-parallel, and if it's unstable equilibrium, if the net force is parallel to the delta x that we have given, then it is never going to come back. Correct?
Yes, sir.
Story hasn't ended yet. That means to study stable equilibrium or unstable equilibrium, I have to create a movie and shift it somewhere and now analyze the force direction, right?
Hmm.
First, I need to first create a movie by shifting it by delta x vector. That means defining the direction of delta x. And then I have to study if the force direction is parallel or anti-parallel. Then only I can know, correct? And also it is net force.
Yes, sir.
Now let us study in this case if it is stable equilibrium or unstable equilibrium. So I am taking delta x bar as positive x direction. Okay, so let us take delta x bar along I cap, let's say.
Sir, so we have to get the force negative.
We have to study if the force is coming negative.
Yes, sir.
Then we will know what science is happening. If we only give everything, that is dictatorship.
Yes, sir.
So let us give delta x bar is along I cap, where I cap is in this direction. Okay.
Yes, sir.
And now understand the net force. Okay.
Yes, sir.
Intuitively figure it out. And we are going to study Q1 and Q2 individually. So delta x I have given along I cap. In this situation, will the electric field E1 will it increase or decrease? That means due to charge Q1, when I go far from the charge Q, will the effect of the charge decrease or increase?
Effect decreases.
Decreases, right? So
Yes, sir.
you know that the electric field E1 will decrease. Second point, will the electric field E2 increase or decrease? If I'm going towards right, that means I'm going closer to Q2.
Hmm.
If I go closer to Q2, will my electric field E2 increase or decrease?
Sir, it will increase.
It will increase because when we are going closer to a positive charge,
That will be for E2. Yes, sir.
the electric field E1, that is the electric field due to charge Q1, will decrease, whereas the electric field due to charge Q2 will increase.
Yes, sir.
Okay,
Yes, sir.
that means the electric field towards this side will increase, whereas the electric field towards that side will decrease.
Hmm.
That means, can I say, does this
It
imply
is more of the negative direction.
does this imply that E2 bar minus E1 bar magnitude of it is going to be greater than 0?
Sir, magnitude is always greater, sir. I mean,
Is greater.
yes, sir.
Acha, you're saying that or let us say like this, instead of magnitude of the entire thing, simply I'll write E2 minus E1. Subtractions of magnitudes will be greater than 0.
Yes, sir.
And E2 is in which direction? This
It
direction.
is negative, so shouldn't it be less than 0?
E2 is increasing.
Yes, sir.
E1 is decreasing.
But E2
Increase.
is in the negative direction.
Yeah, we'll take some example, right? See, direction is fine. Direction is fine. Let
I
us
mean,
just,
the magnitude is greater than 0, but the direction will be along along minus I.
the direction will be along minus I cap. So simply that is where I was coming. That the net force, see, because the field is in negative I cap, that
Hmm.
means force vector is also along negative I cap, right?
Yes, sir.
That means the force vector F net bar is anti-parallel.
It's stable equilibrium.
It's stable equilibrium. Delta
So,
x.
so it's always true for the electric fields.
No, we have to, what I'm trying to show is that we have to always study it this way. We have to always study it this way, individually check the electric fields, see which is increasing, which is decreasing.
Oh, because sometimes charges can be negative.
Charges can be negative. We will do that also. After we do field lines, then again we'll come back to this and we'll do that also. Is this clear?
Yes, sir.
So again I'll repeat from where we have started. We have started, let there be two charges Q1 and Q2, positive charges. Find the point along the extended line AB such that the net electric field is 0. Because the charges are positive, we said the point has to be in between A and B, somewhere in between A and B, and let that distance be x. And the net electric field there should be 0, therefore E1 is equal to E2. Therefore, x is equal to a by 1 plus under root q2 by q1. Correct?
Yes, sir.
The next part for of it is, because the net electric field is 0, I can also say that the net force, if a test charge is placed, the net force is 0 at that point.
Hmm.
That means that position will become an equilibrium position.
Yes, sir.
In equilibrium position, there are two chances. One is stable equilibrium, another is unstable equilibrium.
Hmm.
Stable equilibrium, like you said, is a bowl, and unstable equilibrium example is a reversed bowl.
Yes, sir.
From this example, mathematically, if we have to understand, we said stable equilibrium will come when the net force is anti-parallel to the displacement that is given, and the displacement is given by us external agent.
Hmm.
And it's unstable equilibrium if the net force is parallel to the delta x.
Yes, sir.
Now, to study if it's a stable or unstable, I said we have to individually study E1 and E2, which one is increasing, which one is decreasing, and intuitively figure it out if the net force is it towards along parallel to delta x or anti-parallel to delta x.
Yes, sir.
So taking delta x as I cap, we figured intuitively that E1 decreases, E2 increases. That means E2 minus E1 is basically positive. That means the
Yes,
net
sir.
force is along the negative I cap. That
Hmm.
means the net force is anti-parallel to delta x bar. Therefore, it should be a stable
Stable.
equilibrium. Clear?
Yes, sir.
Xerox.